So today let us start with module 4. Module 4, the title of the chapter is Voltage and Reactive Power Control. So coming to the introduction, first we'll see what is reactive power, what is the importance of reactive power, and then consequences of reactive power imbalance. So coming to reactive power, already in your first year basics you would have studied about reactive power and active power. So whenever it comes to resistive load, the power consumed is basically active, and whenever it comes to inductive load, the power consumed is reactive. You very well know that. If you have to take a recap, if you know that inductors and capacitors are energy storage elements where the energy is stored in the inductor and capacitor in the form of magnetic field and electrostatic field respectively, and during the next half cycle the energy is given back. Energy is not consumed, energy is just absorbed and returned back to the source. So this particular energy or power which is not consumed but just stored temporarily and returned back is called as reactive power. So now here we are talking about the importance of reactive power. Similar to what we studied about active power balance, there is also reactive power balance, which is the total reactive power generated in the power system is equal to total reactive power consumed by the load plus losses. That is reactive power wasted in the form of losses. This is called as reactive power balance equation. In general, we say power balance equation. Specifically, if you go in detail, you will say active power balance and reactive power balance. So this is what is reactive power balance. See, this reactive power balance has a major impact on the system voltage. In the earlier module, we studied about active power balance and it has an impact on frequency. Whenever there is an imbalance in the active power, frequency is going to change. That is, the load and generation, if there is an imbalance, it will affect the frequency. If there is an increase in the load demand, obviously generation will be less, so frequency will reduce. The opposite phenomenon happens when there is a decrease in load demand. Now whenever it comes to reactive power, whenever the reactive power consumption is greater than supply, the voltage is going to reduce. So system voltage always depends on reactive power balance of the system. Next, we'll talk about consequences of reactive power imbalance. Suppose if this balance does not exist, then let us see both the cases. When the consumption is greater than the supply, the other case is when the reactive power supply is greater than the consumption. So first case, consumption of reactive power being greater. Consumption is more, but the reactive power supply available is less. At that point of time, the voltage is significantly going to reduce. So majority of your equipments will stop working if the required voltage level reduces. You very well know that in single phase you need 230 volts, and if it is 3 phase you need 415. Suppose if the voltage drops below the tolerance level of this particular voltage, your equipments will not work at all. So this reduction in voltage happens whenever there is an imbalance in the reactive power supply. And as a next consequence, the power factor is going to drop. When the reactive power consumption goes high, power factor is going to reduce. You already know the relationship between power factor, active and reactive power. PF is equal to P by P plus Q. So if Q increases, obviously power factor reduces. Then another major impact of this excess reactive power consumption is it will always try to heat up the line. The transmission line gets heated up beyond its capacity. It starts to carry current greater than its capacity. Obviously it will get heated up, eventually it may break and it might create an open circuit fault. So these are the possible consequences of one particular case where reactive power consumption will be greater than supply. The other possibility is available reactive power supply in the system being greater than the consumption. Now the consumption is less, the requirement is less, but the supply is more. At this point of time, opposite happens. Voltage will become high. Expected voltage should be 230, it will go 230 plus, whatever may be the magnitude. So the voltage will go high. Even in this case also, your over voltage relay is going to work and again the circuit will break. So there is again a loss of load. And then whenever the applicable voltage level goes on increasing beyond a certain value, insulation will fail. Because of the increase in voltage level, current will be high, then automatically your insulation will fail. If there is an insulation failure, automatically it will lead to short circuit, because there are two lines together with insulation. If the insulation between fails, automatically it will create short circuit in the system. So these are the consequences of reactive power imbalance. So now you have understood what is reactive power, what is the importance of reactive power. Always remember, it has an impact on voltage. If the consumption is greater than supply, voltage will reduce. If the consumption is less than supply, voltage will increase. Next we'll continue with the voltage and reactive power control. So here we are trying to get the generalized expression for instantaneous power, which is a composition of active and reactive power. So here you can see the waveform. In general, voltage waveform happens to be sinusoidal in nature. This is your voltage waveform. Then majority of the loads in the power system are lagging loads. That is nothing but predominantly inductive loads. So obviously current lags the voltage by some angle phi. So the lagging angle is phi, and this is the current waveform, and the amplitude again depends upon the load. And then this is nothing but instantaneous power P, and this P is nothing but product of voltage into current. Everywhere, see here you can see V and I are positive, so power is positive because power is a product of voltage and current. And at this particular zero crossing instant, one of the parameters, either voltage is becoming zero here, obviously power also will be going to zero. And again here current is becoming zero, so power is becoming zero. And here you can see voltage and current both are negative, so negative into negative is positive, so again your power is positive. This is how the pattern continues. So the expression for voltage is given by V of t is equal to Vm sin omega t, which is nothing but root 2 into V sin omega t, RMS value. And I of t is given by Im into sine of omega t minus phi, which represents lagging inductive load. So instead of Im, I can call it as root 2 into I. So root 2 into I sine of omega t minus phi. Next we'll write the expressions for instantaneous power P of t, which is given by product of V of t into I of t, root 2 V sin omega t into root 2 I sine of omega t minus phi. So if you multiply this, you'll be getting 2 Vi sin omega t minus phi. And we are simplifying here. In place of sin omega t minus phi, we'll write it as, say if you take sin A sin B, it is cos of A minus B minus cos of A plus B divided by 2. So it becomes 2 times Vi into cos of omega t minus omega t plus phi, omega t minus omega t plus phi minus cos of 2 omega t minus phi divided by 2. Sin A sin B, cos of A minus B minus cos of A plus B by 2. Again these 2 gets cancelled, and here after simplification you have Vi cos phi minus Vi cos of 2 omega t minus phi, which is again, here it is cos of A minus B, cos A cos B plus sin A sin B, given by cos 2 omega t cos phi plus sin 2 omega t sin phi. Further, if you simplify this, here you can take Vi cos phi as common factor. You will be getting Vi cos phi into 1 minus cos 2 omega t minus Vi sin phi sin 2 omega t. So in this particular formula, if you try to consider the average value in the first expression, the average value will be Vi cos phi. It is actually swinging with twice the frequency, and if you take the average, it will be Vi cos phi. And here, since it is sinusoidal component, average value is 0, you'll be getting the peak value, which is Vi sin phi. So this average value in the which is the first component is nothing but active power P Vi cos phi, and here whatever peak value you are getting is Vi sin phi. So this is how we have got the expressions for active power and reactive power. Next topic is production and absorption of reactive power. So here we are talking about the various sources and the sinks of reactive power. Sources of reactive power, available sources, and then what are the equipments that are going to consume reactive power. So first of all, coming to the alternator or synchronous generator. See, when it comes to synchronous generator, here for representation I have taken infinite bus. Infinite bus is basically a representation which says the voltage always remains constant at this particular end, and this is your generator, and this forms the part of the grid, and here you are having the alternator. So whenever this particular generator is under excited, then generator will act as absorber of reactive power. It will absorb the reactive power from the rest of the system because it is under excited. And again, remember, under excitation means reducing the field current in the generator. If you reduce the field current in the generator, it is said to be under excited. Then that particular excitation current will be drawn from the other part of the system. So at this particular point, it will absorb the reactive power. The generator will try to absorb the reactive power from the grid. On the other hand, whenever the generator is over excited, that is more field current or excitation current is supplied, it will act as a source of reactive power. It will start to supply the reactive power from itself to the grid. So the same generator can act as both source of reactive power, or it can absorb or it can consume reactive power under the conditions. Under excited, it will absorb; over excited, it will supply. Next, coming to overhead transmission lines and transformer. Here we say again, when it comes to overhead transmission line, if the line is heavily loaded, it will absorb reactive power. If the line is lightly loaded, it generates reactive power. You have already studied about short, medium and long transmission lines in your T&D subject. What I refer to heavily loaded coming to that, any transmission line contains the shunt capacitance and series impedance. And you have already studied about medium transmission line having pi and T model, etc. Ultimately, if you take the generalized model, it contains resistance, inductance and capacitance. So when we talk about heavily loaded line, it is inductively dominant. That means on the side of the load, through this particular transmission line is trying to transmit power to the load, and that particular load is highly inductive. When that particular load is highly inductive, this transmission line is said to be heavily loaded. When it is heavily loaded, obviously it will absorb reactive power. And whenever the line is lightly loaded, that is the load that is connected on the other side of this transmission line through which power flows is said to be lightly loaded. Lightly loaded in the sense the inductive load is said to be less than the expected value. Then it is said to be lightly loaded. Under that circumstance, the capacitance effect will be dominant and it will start to generate reactive power. Always in our system we say capacitor tends to generate reactive power while inductor tends to absorb reactive power. So as per the requirement of the system, will either be using inductor or capacitor. So whenever it is a heavily loaded line, automatically it is going to absorb the reactive power, because the consumption will be more, it will be drawing the reactive power. Whenever the line is lightly loaded, it will start to generate the reactive power. And in T&D subject, you already studied about surge impedance loading. I don't want to repeat surge impedance loading. You know what is surge impedance loading. When the loading on the transmission line happens to be greater than surge impedance loading, the voltage is set to reduce. Then coming to transformers. Transformers, you very well know that it just contains resistance and inductance, out of which resistance is negligible. Majority of it is inductive in nature. There is a power transfer taking place from primary to secondary. Energy transfer is taking place, and you are having inductively loaded machine. It's an inductively loaded machine, so it is going to absorb the reactive power from the system. Next, we are going to talk about cables. Cables are most of the cables are capacitively dominant, so they act as reactive power generators. They tend to generate reactive power. And then coming to the load, as you know already, it is inductively dominant. Majority of our load is inductive, so obviously it's going to absorb reactive power. So ultimately we have talked about various sources and sinks of reactive power. So I just want to summarize it once again. Synchronous generator can act as a source as well as sink. It can absorb or generate reactive power based on the condition of excitation. Then coming to overhead transmission lines, depending upon the load that is connected to it, whenever it is heavily loaded, it can act as reactive power consumer. If it is lightly loaded, it can generate reactive power. Transformer always absorbs reactive power. And when it comes to cable, again it is capacitively dominant, it will generate reactive power, and load specifically is inductively dominant, so it will absorb reactive power. Next topic is methods of controlling the voltage. See, methods of controlling the voltage means we are trying to discuss how to balance the reactive power in the system. So here, as of now, I'll just be talking about the different methods available. In the later section, we'll be describing each of them. So the first type is by using the transformers. There are two types, booster transformer and then OLTC. Already you know about OLTC, online tap changers. The transformers that are equipped with tap changing utility will also be coming into aid here whenever you go for voltage control. And the next method is injection of reactive power into the system. This can be done by four methods: static shunt compensation, static series compensation, synchronous condensers, current compensation by series injection. And this is a very famous question in VTU, methods of voltage control. You'll have to describe each of these methods. So regarding the description, I'll come to it later. Now we'll start with the dependence of voltage on reactive power. See, earlier I was telling you reactive power imbalance always affects the voltage, active power imbalance always affects the frequency. So that will be evident in this particular derivation. You will try to understand. So here the other name given to this content is voltage drop along a line in terms of P and Q. Different authors refer to the content by different names. So let us take the system here. Here you can see E at an angle delta. This is nothing but your source, and R and Jx represents the transmission line, and this represents the load. V at an angle 0 is the voltage across the load, and E at an angle delta represents the voltage generated by the generator, and P plus JQ represents the active and reactive power consumed by this particular load. Now here for this particular system we have drawn the phasor diagram, and again I don't want to go into the details of phasor diagram because already you know how to draw the phasor diagram. You're having the inductive load and you're having the transmission line and you're having the source. So it's a simple system. You can start representing voltage and current through each of this to get the phasor diagram. So now what we are interested in is to understand how to arrive at the expression that relates voltage and reactive power, frequency and active power. So from this phasor diagram, here you can see this part is taken as delta VQ and this is delta VP. Okay, so coming to the phasor diagram here, initially I'll be applying Pythagoras theorem here. So that will be done for the triangle OMD. For triangle OMD, I'll be applying Pythagoras theorem. So you know that square of the hypotenuse is equal to square of the opposite plus square of the adjacent. So here this vector OA is nothing but V, which is the voltage across the load, which is considered as reference while drawing the phasor diagram. And the other portion what you can see here, AD, is taken as delta VP. They're using a new variable called delta VP to represent this. MD is represented by delta VQ, and here you are having phi, which represents the power factor angle, and delta is nothing but the load angle or torque angle. So here E square is equal to V plus delta Vp the whole square plus delta Vq whole square. Now here V plus, in place of delta Vp, I am interested in substituting this in terms of, I am trying to represent delta Vp in terms of power factor angle phi. So if you take delta Vp, we have delta Vp, which is nothing but AB plus BD. So AB can be called as IR cos phi. See here, this angle basically will be phi. So this will be the adjacent. So this is hypotenuse. AB is nothing but the cos component of this particular IR. So this will become, sorry, cos component of the triangle. So this becomes IR cos phi. Similarly, BD is same as CN. BD is same as CN, and CN happens to be sine component of this particular triangle. So this will be IX sin phi. So AB plus BD will give me delta Vp. AB is nothing but IR cos phi. BD is nothing but CN, which is IX sin phi. So I'll write it as in place of delta Vp, IR cos phi plus IX sin phi. This is IR cos phi, this is IX sin phi. IR cos phi plus IX sin phi the whole square. And here we have delta VQ square. In place of delta VQ, again, this MD can be written as MN minus DN. I repeat, MN can be written as, sorry, MD can be written as MN minus DN, where MN is nothing but the cos component of this triangle. So I have written IX cos phi minus DN. DN is same as BC. This is sine component of this triangle. So it will be IR sin phi. So IX cos phi minus IR sin phi the whole square. Now in the next step, I multiply and divide by V. Mathematically it doesn't change. So here also multiply by V, divide by V. Everywhere I do the same. Here Vi cos phi can be called as active power P. So this becomes PR by V plus Vi sin phi is nothing but Q. So Qx by V. Same thing here, Px by V minus Qr by V the whole square. In the actual scenario, if you consider V plus delta Vp and delta Vq, this vertical component delta Vq is very much small compared to V plus delta Vq. So you can neglect this delta Vq. In this expression, E square is equal to V plus delta Vp whole square plus delta Vq whole square. Since this value happens to be very small practically, it can be neglected and you will be left out with E square is equal to V plus delta Vp whole square. So E square is equal to V plus delta Vp whole square. Already you know how we have got this, PR by V plus Qx by V whole square. And E square is equal to, this expression is nothing but delta Vp. That's what we had done earlier. So in play, see, initially we had delta Vp, that itself was simplified to this stage. So this PR by V plus Qx by V was nothing but delta Vp. So E square is equal to V plus delta Vp whole square. If you take the square root on both the sides, E is equal to V plus delta Vp, E minus V is equal to delta Vp. So E is nothing but the generated voltage by the generator, V is nothing but voltage across the load. So E minus V will give us the drop across the transmission line, which is nothing but delta Vp. So delta Vp represents the voltage drop across the transmission line. So if you see the diagram here, this is a generated voltage and this is the voltage across the load. E minus V will give you the voltage drop across the line. So let us call this as expression number A. Expression A. Now delta Vp is PR by V plus Qx by V. I come back to the same expression here. See, usually whenever it comes to transmission line in the power system, always there will be resistance, but it will be very small compared to the inductance. So since it is very small, it can be neglected. So you just have delta Vp is equal to Qx by V. And already in expression A, we have E minus V is equal to delta Vp. So in place of delta Vp here, I'll substitute E minus V. So I have E minus V is equal to Qx by V. And this E minus V is nothing but your delta Vp. That delta Vp is directly proportional to Q because the voltage and reactance are constant. Delta Vp is directly proportional to Q. So from here you can understand that the drop in voltage along the transmission line is always directly proportional to the reactive power in the system. Now let us take the other expression delta VQ, which was already derived over there. So here, if you remember, if you go back to the first sheet, here delta VQ was represented by Px by V minus QR by V. I'm taking the same expression again. So delta VQ is equal to Px by V minus QR by V. Again here also, resistance being small, it is neglected. So delta VQ is equal to Px by V. And X and V are constant. Basically voltage remains constant. We assume that reactance is constant. So delta VQ is directly proportional to P, which is active power in the system. Now let us see how this delta VQ relates our active power imbalance. So from the phasor diagram, E sin delta is equal to delta VQ. So coming to the first sheet, this is delta VQ. I'm talking about the triangle ODM. E is the hypotenuse, this is the opposite component, this is the adjacent component. You can represent delta VQ as E sin delta. That's what I'm talking about right now. So E sin delta is equal to delta VQ. So sin delta will become delta VQ by E. So delta will become sin inverse of delta VQ by E. So if you take the proportionality, delta will be directly proportional to delta VQ. So already from this expression D, we know that delta VQ is directly proportional to active power. So from this you can infer that delta is directly proportional to P. Delta is nothing but the load angle or rotor angle. It is always directly proportional to the active power in the system. And load angle is always nothing. You all also, if you remember, d delta by dt will give you velocity. D square delta by dt square is nothing but acceleration. So d delta by dt is nothing but velocity. If you take the scalar quantity is nothing but speed. So speed and frequency are related. So obviously power and frequency are directly proportional parameters. So this is how the active power is related to speed or frequency of the system. And previously we have understood that reactive power depends upon voltage, or reactive power is directly related to voltage in the system. So with this topic I have finished 40% of module 4. Next I'll continue in the coming video.